like to first thank the CRIBIQ organizing committee for inviting us. So, as Mr. Ennis mentioned, my name is Antoine Charbonneau. I'm VP Business Development of CelluForce, and hopefully after my presentation, I will have conveyed a little bit of my excitement about our product, which is cellulose nanocrystals. This is the agenda that I propose. First, I'm going to present a few introductory slides, put some context and perspective. Then I'll go straight into the properties, and as I describe the properties, I'll mention some applications, talk about safety, which is an important point for a nanomaterial, and then I'll explain a little bit more about the company itself and how we develop applications. So in 2014, the intellectual property and the science group from Thomson Reuters evaluated patent applications and various papers in their Web of Science publication, and made some predictions for 2025 as far as innovation is concerned. And one of their 10 findings was that cellulose is in and petroleum is out. So cellulose really is a material of the future. It's the most abundant naturally occurring polymer. It's bio-based and sustainable. And Canada and Quebec are well positioned to capture that with a very well developed research network and a solid industrial base. Again, to put things in perspective, there's a lot of different cellulosic materials. Just here looking at the scale here of the fibers and particles. So at the macro scale, we have chemical pulp fibers. You can actually see them as we go smaller. So micro, we have microcrystalline cellulose, microfibrillar cellulose, even smaller cellulose nanofibrils, which we just learned about. And even smaller than that, so we're talking in the order of magnitude of about 100 to 200 microns, 100 to 200 nanometers, cellulose nanocrystals, which we manufacture. So just a word on semantics. So nanocrystalline cellulose, cellulose nanocrystals, nano whiskers, they're all interchangeable terms. Okay, so it can be a little bit confusing, but I tend to use cellulose nanocrystals, although our product name is CelluForce NCC, all right? So just want to clear that. So what we do is we start off with craft fiber, so no lignin. And we do a sulfuric acid leaching or extraction, if you will. And what happens is that the amorphous regions of cellulose are dissolved and you're left with the crystalline regions. So here you see, so we go smaller and smaller, and here you see the whisker shape, so the rods that are separated from the amorphous cellulose. So talking about properties, so we're talking about a nanomaterial that has very peculiar properties. The first one is self-assembly. So basically, these are little whiskers or spindles, if you will, and they're highly charged on the surface. So this allows the formation of what is called liquid crystals. So basically, that's a fluid with domains of order in it, and those domains will depend on the concentration of the solvent. In this case, it's the water. As the water is extracted, the spindles will orient themselves, and each layer tends to be oriented in the same direction. And this allows very effective suspension of other materials. So we see this being used in coating applications, for example, where suspension of other materials is very important. It's extremely strong and resistant. I mean, very high temperature resistance. We see this is a huge benefit in oil and gas applications, where, I mean, the deeper you dig, the higher the temperature. And it's very strong. It's a strong material, so it has a very high crystallinity. I mean, we're making cellulose nanocrystals. They're purely crystalline. Very high stiffness and tensile strength. So the whiskers actually have the same tensile strength or same strength that's in the same order of magnitude as metals and their alloys. So it's the same thing as Kevlar. So it can be used to strengthen materials. This is actually one of the applications that we're actively developing. And there's a lot of interest, for example, in polymers. The material is thixotropic. So it's shear thinning. And this is a little bit counterintuitive. So basically, if you don't apply any shear to it, the material is very viscous, and the more shear you apply, the more easily it's going to flow. So this, again, is something that's very useful in, for example, oil and gas applications where you need the interface to be quite stable, but the material needs to be able to be pumped easily. So yeah, here the explanation. So the material can flow easily, which is a useful property. It's very surface active, so that property can be used to graft other molecules onto the surface, and we can extract a lot of different or use it in different applications. The commercial version we have right now is a sulfate salt, so it's very hydrophilic. But we have the capability of modifying the surface in order to make the particle more hydrophobic. So a little illustration here of what can be done. And here's an actual example where we've grafted PDMA on the surface of the CNC. So once the epoxy cures with the hardener system, the CNC helps avoid propagation of stress. So you can see significant increases in toughness. I mean, we're talking 120%, tensile strength in the order of 100%, tensile modulus and tensile strength also 20%. So we like to think that we're putting a little bit of wood in hockey sticks because sports gear is an area where these properties are useful and sought after. Continuing with the properties, so it's an electromagnetic material. It's charged, and it will actually orient itself with the Earth's magnetic field. And this is because the functional groups impart a charge onto the particle and imparts it to the crystal. And this can be used in certain applications to orient the nanoparticles to give isotropy to certain systems. And it has a very high surface area. We're talking in the order of 550 square meters per gram. I mean, these are the dimensions of the nano whiskers and aspect ratio of 20. So it interacts substantially with its surroundings. And we're talking about the nanoscale here, so it's not necessarily intuitive for all. I often get contacted by customers that I actually should be referring to you that visualize the nanocrystalline cellulose as being a type of fiber, and it's not. It's really a crystal. It interacts strongly with the environment where it's located, but it's definitely not a fiber. And the last property is it's actually quite optically active. This is actually the initial research that was done on CNC, was to look into the optical properties. So as the water is removed, the CNC will form layers, and they're ordered layers, and the distance between the particles is in the order of the wavelength of light, and it does interfere with light. So there are multiple applications where that can be used, for example, in coatings to shift the infrared spectrum. So CNC can be used for that. Talking a little bit about safety, so I'm glad to tell you that CNC is safe. It's made from wood sources that are certified by the Forest Stewardship Council. And there's a lot of tests that have been done to certify that it is not toxic to animals. We ship it, or the way it's dried, we spray dry it. So the agglomerates are about 30 microns in size. So just standard safety equipment can be used. And it has been added to Canada's domestic substance list. So it can be produced and shipped without any restriction. And we have confirmation that, since it's considered a natural polymer, we don't need to classify it within REACH in Europe, so we can ship it also to Europe without any issues. And same thing for the United States. We have the same confirmation from the EPA. So that's the product. So I'll tell you a little bit more about CelluForce. So our head office is in Montreal, and we have a plant in Windsor. It's actually at the Domtar site. The plant is sized for 300 tons per year. So we are the premier worldwide manufacturer of cellulose nanocrystals. So we're actively developing applications because the bottleneck is not on the production side. It's really on the application side. This is a novel particle. There's a lot of scientific papers written about it, but I'm pursuing industrial opportunities, and these need to be developed. This is an exciting year for us. It's the first year where we've had revenue, so $200,000 this year. Yay. Right now we're 20 employees, and we have 3 shareholders, and you might recognize some names here. So first off, the company, and I'll go into the history a little bit later, but was founded with Domtar and FP Innovations to basically leverage FP's development of CNC. And in 2015, Schlumberger, so the giant in oil and gas services, joined us on the equity side. And they're actually also, we're obviously developing a lot of applications with them and going to go commercial very soon. So this is the history of the company. So CNCs, cellulose nanocrystals, there was initial research at McGill in the 40s and 50s, but it was mostly exploratory, and as I mentioned earlier, looking more into the optical properties. And as they garnered more interest, FP Innovations continued the development. Our CTO started on the project in 2005-2006, with the first CNC pilot plant at 2 kilograms a day. And in 2011, the company was officially founded, and we started construction of our plant. At the time, it was 100 tons a day. Now we've moved to 100 tons per year. Now we've moved to 300. 2012, the plant was operational. From 2013 to 2015, we went through the valley of death. So little hiatus with our activities, looking for financing. But fortunately, with Schlumberger joining us, a new management team too, now we're actively developing applications. I joined the team 3 months ago, so apologies. I haven't done this presentation too often, so please bear with me. We have a large patent portfolio, both internally and through our partnership with FP Innovations. And we really, since we already are at, we're the first one with such a large capacity, we want to hold on to our leader's advantage. So we have a portfolio of over 50 patent families. Here you see a graphical representation of other players, but CelluForce, this includes the FPI patents, really represents a substantial portion of the environment. And we want to keep it that way. So our innovation approach, we are, of course, we have a lot of capacity, so we are tackling this on multiple fronts. There's the fundamental understanding, and I'm a little bit less concerned with that. I'm more looking into application development, and the production technology must follow because it's a highly reactive surface, so we can tweak it, we can modify it, but it has manufacturing impacts, so we need to get everybody on board to make sure that we're aligned. We develop both internally through our own facilities and through FP Innovation, but other industrial partners as well as through academia. We really have a large network of partners helping us to advance the developments. And so how do we go about doing this? We basically focus on a few key applications, namely oil and gas through Schlumberger. They have exclusivity as part of the equity deal we did with them. But at the same time, we're looking at paper, adhesives, plastics, paints and coatings, as well as cement. So these we prefer to go through joint development agreements with the partners. There's still a lot to learn about the behavior of the CNC. And sometimes it's partner driven. This is the case with electronics and personal care. We basically have a pipeline with, you see here, this is what we call, well, this is the TRL, so technology readiness level. This is used quite significantly in industry. It was started off by NASA, but we also added an axis commercial development level, and we have a third one which is manufacturing development level, and we try to basically fill the pipeline with the opportunities, but having mapped all these axes and making sure that we have the required resources to advance them. So we're using a systematic approach to develop the various applications. So what's next? We're anxiously looking to commercialize specific applications, specific opportunities. It's going to happen soon. And looking to ramp up production. Our goal is to maintain our position of leadership. So we'll have a 300-ton per year plant, and our goal is within the next 3 to 5 years to build a plant that's 10 times larger and really supply this novel material to industry. So with that, I thank you for your time, and I'll be glad to answer questions on the panel. Thank you.